Starting with the introduction, the purpose of this lab is to observe an object in oscillating motion and create a model to predict the motion of the object. Furthermore, the actual data and model are compared against each other. The lab followed the following steps. Step 1, data extraction. Step 2, model creation. And step 3, observation and model comparison. The result shows that the model closely mimics the observed movement of the object, but there are slight differences in the values due to the model failing to take factors such as friction or drag into account. Onto the model. These are the three models created. The first graph shows the change in energy versus time. The second one shows x position versus time. And the third one shows y position versus time. The first main physics idea used is velocity and momentum. Velocity is a rate of change in an object's position with respect to the amount of time passed. Momentum is a vector quantity calculated by multiplying the mass and velocity of a system. And lastly, according to Newton's second law, the change of momentum divided by the change in time equals to the net force acting on a system. The energy principle shows that if a system is isolated, the total energy of a system is conserved. The kinetic energy is an energy an object has due to its motion, and the formula for that is 1/2 mv squared. Gravitational potential energy is an energy that an object possesses due to its position in a gravitational field, and the formula for that is negative gm over r. And lastly, Hooke's law tells us that the force exerted by a spring is negative kx, in which k is a spring constant and x is a stretch, and the spring potential energy is calculated by 1/2 kx squared. Now to the experiment. Tracker was used to extract the object's position and corresponding time, which was made into a table and graph. System was a spring and mass. Surrounding was everything in the room excluding the spring mass system, such as the air. Initial conditions were starting position negative 0.109, comma negative 0.592, comma 0 meters. Initial time was 0 seconds. Initial velocity was 0.09716, comma negative 0.0737, comma 0 meters per second. Now to the code. GlowScript's Web VPython program was used to create a computational model that resembles the observed motion. The assumptions made to create the model were mass of the system 0.42 kilograms, spring constant 6.83 Newton per meter, relaxed length of the spring 0.123 meters, net force equals gravitational force plus spring force. Line 48 was changed for the mass. Lines 51 and 52 were changed for initial position and velocity. Line 82 was changed for spring constant. Line 85 was changed for the relaxed length of the spring. Lines 88 to 90 were changed for the stretch of the spring. Lines 93 to 96 were changed for the energies. Line 114 was changed for the gravitational force. Line 117 was changed for the spring force. Line 120 was changed for the net force. Line 124 was changed for velocity. Line 26 for position. Lines 129 to 131 were changed for a stretch of the spring. Lines 137 to 144 were changed to update the energies. These are the results of the code. The top left shows how the spring mass system moved throughout the code. The bottom left shows change in energy versus time graph. The top right shows x position versus time graph, and the bottom right shows a y position versus time graph. The final graphs were first change in energy versus time, second x position versus time, and third, y position versus time. The change in energy versus time graph shows the change in kinetic energy in blue, the change in gravitational potential energy in red, the change in spring potential energy in green, and the change in total energy in yellow. The x position versus time graph shows the predicted and observed x position versus time. The similarities between the two are that the overall shape are very similar, and both show oscillating movement. And the differences are that the model predicts the period to be longer, and the model predicts the position to be smaller than the actual observed data. For the y position versus time graph, the predicted and observed y position versus time are also shown here. And the similarities are that the overall shape are very similar, both show oscillating movement, and predicted periods are almost identical. The differences are that the model underestimates the y position when the spring is at its shortest in each period. The model overestimates the y position when the spring is at its longest in each period. Now to the discussion. Possible rooms for error were in various dissipated forces not being taken into account, such as drag or friction, inaccurate clicking on tracker, and bad video quality. For the first what does it mean question, yes, it is satisfied looking at the model system. The energy principle appears to not be satisfied as the change in total energy is non-zero. However, if you consider the fact that the system is not isolated and dissipated forces are doing work on the system, the non-zero change in total energy is explained. For the second question, the period of oscillation in the x position is about 1.6 seconds, and the period of oscillation in the y position is about 1.5 seconds. The two differ as oscillation in the x position resembles a pendulum, and the oscillation in the y position is a spring motion. This makes it so that the period in the x position is determined by the gravitational acceleration and length of the spring, while the period in the y direction is determined by the mass and the spring constant. Now to conclusions. After going through the process of making observations on oscillation and making a model to make the model, these are the findings. Anticipated forces do not negligible amount of work on an oscillating system, and the period of a pendulum is determined by the length of the spring and the gravitational acceleration, while the period of a spring oscillation is determined by the mass of the object and the spring constant. Thank you.